So previously we calculated the position vector and how to calculate velocity at a particular point, oh sorry, particular time stamp, time t. Similarly, for the rolling part, like this, that was for the transitional part. Like for the rolling part, we have orientation. So we represent orientation as theta, and it's the same belong to third dimensional space. So at a particular point time t, we have roll value, pitch value, and yaw value at a particular point time t. These are nothing but roll, pitch, and yaw values. So, like we created linear velocity previously, here we calculate angular velocity. Similar way, theta dash, theta naught, it's same in third dimensional space, belong to third dimensional space. Uh, why this are to third dimensional space? We already know. This is a time domain, and this is a uh, the domain, previously it was position, now it was orientation domain, orientation at particular time t. Here it is velocity at particular time t, angular velocity, more specific. Angular acceleration would be represented as like this. So uh, like force, we know uh, the angular thing has torque. For example, previously, if this is a box applying, we are applying some force, it will have some transitional motion. It's linear motion, but now it's a angular motion. For example, this is a hinge and door is attached to it. We apply push to move it. It will move in angular way. So yeah, here comes the torque. Torque is F cross R perpendicular. F is the force or push we are applying here, and R is the perpendicular distance, this distance from the axis of rotation. So yeah, uh, we have torque, Newton meter, I, moment of inertia, kg per meter square, and alpha, angular acceleration, just like we have had F equals to m or radian per second square. So yeah, just similarly like previous, we can write these formulations. Angular acceleration, we can write it as like this is alpha, and the final angular velocity at some time point of time t, like the zero thing is the initial velocity, integrating it over some time t, uh, the tau value is the w variable. So yeah, we can write it at like this. So why we are calculating these formulations? It's to simply to model or to design a helicopter on the problem basis of what we are expecting. So yeah, so here comes model order reduction part. Here we do what? We will reduce our problem into only that statement which we want to see. For example, suppose if we have a helicopter, it's its tail rotor. Suppose if the helicopter doesn't have tail rotor, then what happen? It will only have a head rotor. So what happen is the this is for counterbalance. What does it mean by counterbalance? Like the torque it is providing in the direction the torque head rotor provide in the direction the tail rotor torque is in the opposite direction of the head rotor torque. So these two opposite rotations cancel each other, so that stabilizes the helicopter. What if there is no tail rotor? The counterbalance is not there, and the helicopter spins or rotates like this uh, uncontrollably due to torque induced by friction in the rotor shaft. It will spin uncontrollably. So yeah, if we want to study this problem, I will say I only want to look about this particular problem, which is what apply torque using the tail rotor to counterbalance torque on top rotor. So what does it mean? It is saying that I only want to study why it spin around itself. Why this tail rotor is important in a helicopter. So the what the problem is saying that I only want to study that XYZ. No position is needed. So as I only want to spin, I don't require the XYZ linear accelerations. I don't require roll or pitch motion. No need. What I only require to study is the yaw motion. I want to study this only. So what happened? We had six variables and now it's reduced to one variable because I want to study that variable only. So the problem is reduced, but here are two assumptions in the problem. What are that? Helicopter position is fixed. That means x equals to constant, y equals to constant, and z equals to constant. So we don't look into these parameters. And second assumption we have to take is helicopter remains vertical. Yeah, so the roll motion is zero and there is no pitch motion there because the helicopter is vertical. It will yaw only. It will spin like this. So we need to study this only. So the equation of torque we wrote, torque about x, y, z. If we do a matrix formulation, it will look like this. We differentiate the these are the moment of inertia values around the axes, and these are the angular velocity about x, y, and z. So to get the torque values, we multiply moment of inertia with angular velocity and take a derivative of this, and we only are looking for yaw values. So this will simple up to the y values only. So we can write it as this. This is the model we want to study. We will simulate to look upon values. We will fed some values to it, and we will get some plots and analyze its output using Simulink. So this the equation simplified. We will going to study using Simulink, and how we create this in Simulink we will see in next video.